Okay, so this is the beginning of an advanced concepts presentation to deriving the Michaelis-Menten equation. All right, so let's go ahead and proceed. I am going to be reading off some notes I'd made myself, and I have already written a couple of things. So let's go ahead and discuss what I've written here. So we see E is the enzyme, S is the substrate. Now they join together in what is known as the enzyme substrate complex or the Michaelis-Menten complex. All right, so up here, this is reaction 1, and it's going to have arrows going in this direction and then arrows going in that direction. All right, so if you notice that the arrows I have drawn, they do go in both directions, and this is due to the fact that the reaction can proceed in both forward and backward. All right, so now for the second equation, now we do have the enzyme substrate complex here that was created in equation 1, and this enzyme substrate create the enzyme plus the product, right? So the second step leads to the enzyme and substrate complex to break apart, which leads us to having the enzyme and product P, as you see here. There is a single arrow, right, depicting this reaction. Due to the lack of product being formed, there is not enough for a backwards reaction. So this product here, there is not enough for this to go backwards. I believe if you remember in, I think it was Chem 2, is where we have those forward and backward reactions. That's at least the where I can remember it from. All right, so we're gonna go ahead and move forward. These are a couple of variables that I'm gonna go ahead and add to what I've written above so that we can understand more about the equations that have been utilized here. So as you can see, this equation up here is going to have K1, right? Because it's going to be creating a product. So it's going to be a positive 1. Then we have K negative 1. And I think that you can understand that it is negative 1 because we are going backwards. All right, and then this one down here is going to be K2. And if you can see here, I wrote that K1 is rate constant of forward first step, all right? K negative 1 is rate constant of the backward first step, negative 1 because we're going backwards. K2 is rate constant of the second step. All right. Now, to verify the mechanism is valid, we add reaction 1 and reaction 2. Right, so if we add these two together, these two reactions together, let's go ahead and add a line here. So some things are going to be canceling out here. So ES is going to cancel out on either side, as well as the enzymes. And again, ES is enzyme substrate complex, and the E stand for enzyme, right? So the enzyme up here in equation 1 is going to, or reaction 1 is going to cancel with this one. So what are we left with? We are left with S. So the substrate creating product, right? So we have this S, which is substrate. We have P, which is the product. Okay, so as you see here, enzyme plus substrate is going to react and create the enzyme substrate complex, which is then going to react and create the enzyme plus the product. Now, the creation of the enzyme substrate complex is equal to the sum of all reactions, decreasing its concentration, right? So as you see here, the enzyme substrate equals K1 minus K minus 1 minus K2, which is equal to 0. Now the proper equation utilized is going to be this one down here, which is the instantaneous rate of change, which is equal to 0, which equals the reaction of concentration concentration K1 multiplied by the enzyme multiplied by the substrate minus K minus 1 multiplied by the enzyme substrate complex minus K2 multiplied by the enzyme substrate complex. Now the difficulty that we have with this is we do not know the unbounded enzyme, what this is. Right, so to solve this, we use this equation right here, which is E sub t must then equal the concentration of E, which is the unbound enzyme, plus the concentration of ES, which is the bounded enzyme. Right, so if we rearrange this equation, right, so if we rearrange this equation to give us what we're looking for, so we have the unbound enzyme. We want to figure out what is this unbound enzyme. So we're going to go ahead and rearrange the equation here. Right, so T minus this is going to give us the value of the unbound enzyme. So what we're going to do now is we are going to sub this equation into E that we have here, right? Because as we see here, this E is going to equal E sub t minus enzyme substrate. So this is going to go in place of E. I'm going to go ahead and write that out. So if we go ahead and distribute the K1, what we are going to end up with is, go ahead and try and do this without the phone defocusing, K1 multiplied by E sub t multiplied by the substrate minus K1, let me write a little smaller, maybe, enzyme substrate complex multiplied by the substrate minus K minus 1 multiplied by the enzyme substrate complex minus K2, which is also multiplied by the enzyme substrate complex. Our goal is to find the value of ES, so we are going to solve for ES. Right, so we're going to go ahead. Let's see. ES, right? Sorry, my pen is like being weird. All right, so grab the blue one. Sorry about that. So K1 multiplied by the substrate plus K minus 1 plus K2, right, which equals K1 multiplied enzyme and substrate. Okay. So like I said, we're trying to isolate ES, so we are going to rearrange this and make it into a division equation. So we're going to pull out the enzyme substrate complex over here, and we are going to place K1, right? So we're going to pull this over here. K1 E T multiplied by the substrate and K1. This one's going to be going down here. Okay, 1. Okay, so I'm running out of a little bit of room here. All right, so now we're going to rearrange this expression to isolate the rate constant and then replace these constants with a new constant, which is called the Michaelis constant. And Michaelis constant is where we see this in all of the labs that we've been doing recently. All right, so the way we are going to do that is, and I'm going to try and write here so that you guys can see what I'm doing on this end. It's going to be enzyme substrate. Sometimes saying it out loud kind of helps me. Right? Now what we're doing here is just kind of algebra pretty much. So. All right. So this Km is going to fit into this portion here. So the way we're going to do that is over, and like I said, we're replacing that portion plus S. And all right, so if you see that on the presentation 2, you do see an equation that is Km, which is the Michaelis-Menten constant. It's equal to K minus 1 plus K2 over K1, which is why we arrange everything to fit this equation so that we can go ahead and fit in the Km in this portion right over here. So that's where the Michaelis constant comes in. Okay, now we're going to substitute the value of ES. All right, so now we're going to substitute the enzyme substrate complex into the rate equation. Now K2. All right, so we have our equation here. Now keep in mind that the instantaneous rate of change for product P is the function of its reactant, right? So and we do know that there is only one reaction for K2, which is ES. Now, we already have an equation for ES, which is over here. So we're going to go ahead and substitute yet again. All right, so we're going to substitute ES into the rate equation, right? And if we keep in mind that K2 is equal to the catalytic constant, so it can also be referred to as Kcat. Kcat technically defines how many molecules an enzyme can work with per second, right? So this is then going to equal Kcat ET, with the substrate. All right, so Vmax is equal to the total enzyme concentration multiplied by the catalytic constant. We substitute Vmax into the equation to get the final form of the Michaelis-Menten equation. Check plus.